When you play the play round, you get that. Killing is just the guns just starting hard. So everything you can say will be
Using multipliers.
Hello, Gillian. What we're doing is trying to prove that AN, the alternating group of permutations of n elements, even permutation, is simple. And simple means that it has no normal subgroups other than, of course, the one element subgroup and the whole group itself. They're always normal. But those are trivial, so those they don't count. Is that readable? It was too dark here, so I switched the light on. Okay. Now, what we did last week was this lemma. It says that if you take if you look at all the three cycles in the alternating group, then they generate the whole group. Okay. So that was the first step on the way to the theorem that there are no non-trivial normal subgroups. So today we're going to finish this. Tomorrow, well, I hope we're going to finish it. Tomorrow we'll do a bit of an examples or exercises class with both Killian and myself present, and we'll give you the coursework as well tomorrow. And we can tell you something about the coursework, perhaps, if you have any questions by then. Otherwise, we'll do exercises. So let's go on and try and prove it, and then we can go to bed again. So we had this lemma that's generated by all three cycles. So the next lemma, I'll call it lemma 10 point, sorry?
9.
I'm going to call it 10.8.5. And it says that if n is greater than or equal to 3, and if you take I and j in the set of, well, the things that the alternating group acts on, so they 1 to n, and if they're distinct, then if you look at all the, okay, so you look at all ij, a, it's a cycle of length 3, in which I and j are these two fixed numbers, different numbers, and a, so you look at all the cycles that start with these two fixed numbers, okay, and a is any number in the rest, so it's 1 to n minus I. Okay. It's fancy notation. And this generates the whole group. Have you deciphered the notation? What?
I'm seeing the curly brackets IJA, and then all my brain's going as fajitas.
Anyway. So lemma 10.8 said that if you take all three cycles in AN, what they generate is the whole group. Okay? And this says you can actually take many fewer free cycles, because you can fix the first superposition and you just run the remaining element in the free cycle through all the remaining elements of the set 1 to n. When you take these n-2 free cycles, they already generate the whole group by n. Okay, that's the lemma. What's the proof? The proof is, okay, well, by the previous lemma, so lemma 10.8, an is generated by all free cycles. Okay, so that means all we need to check is that every free cycle can be written as a product of 3 cycles in this form. Okay, so we only need to check that any free cycle is a product of some free cycles of the form ija. Because if they are, then we can generate all 3 cycles, and if we have all 3 cycles, that generates the whole group. So that's the idea. So what can a free cycle look like? So if it contains both I and j like this, then yeah, this is ija, and there's nothing to prove. If it looks like this, I, A, J, is that generated by some kind of ij? This is yes, because this is ij a squared. Do you believe me?
I promise that SL3R is not a subgroup from the R.
So ija, if you do the square, well, I goes to A, J goes to I, A goes to J, because they skip one in the square. What else can we have? So these were all the 3 cycles that contain both I and J. Okay. Then there are some 3 cycles that only contain one of them. So IAB. If you have IAB, then you can write it as IJB times IJA. No, that's rubbish. IJA squared. You care to check? So if I goes to A goes to J. What am I doing?
We'll have to do the square bit first.
Oh, I goes to A goes to A. Where does A go? A goes to J, goes to B. Where does B go? B is not there, so B goes to I, so that's this. And where does J go? J goes to I, goes to J, so it's correct. Then if it's JAB, then of course, you can do IJB squared, IJA, whatever. And finally, ABC. So if none of I and J is there, then you can write it as IJA squared, IJC, IJB squared, IJA. Apparently, I think I checked it some time ago and it worked. So if you don't believe me, check it. If it's wrong, I'll have to fix it. Lemma is proved. Okay. So what's in it? Good. Now, the lemma you wanted, 10.9. Well, the reason I called that one 8.5 is that it's not a lemma in the book, so I'm keeping the same numbering as in the book. And he just puts it as part of the proof of lemma not 10.9, but I think it's worth doing it as a separate lemma because it's then easier to pass. What's lemma 10.9? So if we get a normal subgroup of n which contains, if n contains a 3 cycle, just one, then it's already the whole group. Okay, so proof. Suppose that n contains a 3 cycle, and we'll call the elements in the 3 cycle I, j, and a. Okay, so if a is 3, little n, then we already have all the 3 cycles of the form ija, because there's only one. If n is greater than 3, then we take a number which is not I, which is not j, and which is not a. And what we want to prove is that ijb is also in n. And like this, we'll get all the ij somethings. Okay? And by 8.5, 8.5, we already have that if you have ij, all ij somethings, then it generates the whole group. So if it's a subgroup and contains all the ij somethings, it has to be the whole an. So we want that ijb is an n. Then by lemma 10.8.5, n is an. So how do we get that? Nasty stuff. Now, what is okay, so if I do ija squared, is that in n?
Yes.
Yes. It's in n because ija is in n, and n is a subgroup, so the square has to be in n as well. If I do ij ab, ija, is that in n? Well, I don't know. But if I do ab, ij, is that in n? Well, I'll give you a hint. This is ijab, ija squared, ijab inverse. Yeah. In fact, we don't have to swap them because they're disjoint, so change this order. However, this is in n. Why is this in n? Because pardon, so then
The inverse, I mean, the end will refer anything else that wasn't in the center. The center of it is in there.
wow. Yes, but why? That's not well. Okay, so you take something. If you have an element of n, you multiply by something that might take it out of n, and then you multiply it by the inverse from the other side, and that puts it back in n. Is that what you said?
Pretty much, yeah. No.
Well, is that always? Why is that? Why is that? Any idea? Yes. No?
Yeah, that's it.
Is that true for any subgroup?
No. It has to be one of the words that Paul and back up.
Commutative or associative. Commutative.
Commutative.
No,
The other one.
it doesn't have to be commutative. But it's one of the defining, well, look at the definition of the normal, or the theorem 10 point, whatever, 10.3 or whatever it was.
Subgroup areas are normal in G, or little g in big G, G and G inverse is within n.
Yeah. In other words, if you take an element of n and multiply it by any element of G from one side and its inverse from the other side, you get an element in n. And that is because n is normal. If n wasn't normal, you wouldn't get it. What? Okay, now give me what this is. So, I, where does I go? I goes to J, goes to I, goes to J. J goes to I, goes to A, goes to B. B goes to A, goes to J, goes to I. A goes to B, goes to A.
How come when you're squaring something, yeah, how come it just goes from the back to the next one rather than going from A to I?
It jumps over one.
Because it's just, yeah, because it's square. Is that just the rule of squaring?
Well, you're moving
Cycles,
two to the
yes.
right because you're jumping back. It's only
Yeah,
three,
well,
it's -1.
Ah.
Not you're working much like 3.
But if you had a long cycle, if you take its square, it's like you do it twice. Yeah. So the first time it moves to the next one, and the second time moves to the next one. So it's like jump over one. Okay, so this is it for 10.9, and now, oh my goodness, now we have to work hard. Now we have to work hard. Now the hard work is hidden in lemma 1010. Which says that if n is at least 5, if n is a normal subgroup of an, and n is not just the identity, then, can you guess what? Then n contains a free cycle. And then if we prove this, then because once it contains a free cycle, it has to be the whole AM, and that will prove that there are no non-trivial normal subgroups. So this is the remainder of the proof there. Okay. So okay. N contains sigma, which is not the identity. It's not the identity. Then it can be written as a product of disjoint cycles. We know that from the chapter about permutations. There are several options. Number one, sigma is a free cycle. Number two, I'll just list the options first. Sigma contains a long cycle at the back, so it's tau. I never know how to. It's tau times A1, A2, AR with R bigger than 3. Third option. Well, because they're disjoint, so it doesn't matter what order you write them in. So this is just that sigma has some cycle that is longer than 3. Okay. The third option is that, well, maybe it doesn't have a long cycle, but it has two, 3 cycles like that. Okay. And there is no long. Long. And the fourth option is that you don't have at least 2 free cycles, and in that case, you can either have 1, but then tau is the product of disjoint 2 cycles. And the fifth option is that sigma is 1, A2, A3, 4, and tau is the product of disjoint 2 cycles. And that's everything. That's exhaustive now. So now we need to show that in each of these cases, if you find an element that is, well, it's an AN, either it is a free cycle, or it has a long cycle, or it has at least 2 free. It doesn't have any long cycle, longer than 3, but it has at least 2 free cycles. Or it doesn't have 2 free cycles, it only has 1 free cycle, and the rest of them are 2 cycles, or it only has 2 cycles. Okay, and there's no other option. Okay? Because how could that be? So now we want to prove that in each of these 5 cases, there is a free cycle in the group. Which is the easiest? It's quite right. So we want to show that in each of the cases, N contains a free cycle. One, nothing to prove. 2, oh dear, now it's starting. Okay, so N contains sigma inverse A1, A2, A3, sigma A1, A2, A3 inverse.
Element of N contains sigma minus.
Yeah, N contains sigma minus 1.
It's a backwards in, not an
It's
arrow.
like backwards in.
Oh, right. I've never seen that before.
Yeah.
I have not.
Well, okay, so I've been using it, and I'm. You've definitely seen it all these merits.
Okay, no. It's okay, so now this is a disaster. Okay, so what is sigma inverse? Sigma inverse is A1, A2 up to AR inverse, tau inverse, then A1, A2, A3 is there, sigma is tau, A1, A2, AR. I've run out of paper. And then this times A1, A2, A3 inverse. And to get back with my notes. So in case 2, sigma is that thing over there. So I'm just putting, oh, right, so first maybe, is it clear that this is in N, this product? I'm claiming that N contains this, but maybe you don't trust me. There's something in your way, I don't know what this is. Is it that? No. Better. Okay, sigma is in N is normal. You times it from the left by something, from the right by its inverse, it's in N. Sigma inverse is in N because it's a subgroup. Times them all together, you're in N. Then sigma inverse is this because sigma is that. A1 to this remains, sigma is that. Inverse of that cycle. Now if you work this out, what are you going to get? Okay, this is a product of disjoint cycles. So tau does not contain any of these elements, A1 to AR, so it commutes with everything else. So these two taus, they can move together and vanish. But the rest is not so simple. Okay, so the inverse of this is A1, that's kind of like going backwards. So A1 goes to AR, goes to AR minus 1, all the way down to A2. Tau vanishes, A1, A2, A3. A2, AR. A1, A3, A2. And when you work that out, so A1 goes to A3, goes to A4, A4, what does A4 do? A4 goes to A5, goes to A4. Am I doing it right? No. Wrong. Again, start again. Where does A1 go? A1 goes to A3, goes to A4, goes back to A3. That's better. Where does A3 go? A3 goes to A2, goes to A3, goes to A1, goes to AR.
That's a 3 the second one.
That's a 3. Sorry.
It's okay.
Where does AR go?
Yeah.
AR goes to A1, goes to A2, goes to A1. Okay, so that's one cycle. Where does A2 go? A2.
Yes.
So A2 goes to A2. Where does A4 go? A4 goes to A5, goes to A4. Where does A5 go? A6, A5. So all the rest of them go to themselves. So this is a free cycle.
Oh, it's sat there, like, I'm trying to work them out.
Hint which I think is in the 3 cells.
So massive.
How would you come up with that?
Yeah,
Years of trying. So if you fear this proof is going to be on the exam, you just have to remember it. It's probably not going to be on the exam.
Oh, that's how
Well, that's probably only going to be proofs that you can actually.
remember.
Well, yes. Well, Even if you don't remember them, you can probably find them.
Split it all there.
Okay, in case 3, what's case 3? So there are 2 3 cycles in sigma, and the rest of them, well, oh no, there are 2 3 cycles, and the rest of them we don't know, but there's no long cycle. Okay? So in this case, how much time is left? Okay, I'll make it quicker now. I won't check all the steps, I'll just leave them for you to check. So sigma inverse A1, A2, A4, sigma A1, A2, A4, inverse. Okay, same reason as before. Sigma is in N, times by something, and it's inverse from respective sides. You get something in N because N is normal. Times it by something in N, you get something that's still in N. Okay? Yes, Jordan?
Where's A4 come from?
Or in case 3,
A1, A2, A3.
A4, A5, A6. So that's where it's come from.
It's just in there.
What?
It's just in there.
Oh, well, why do I have to go to something that I explained to you? Okay, if you have sigma, okay, sigma is any element in AN, actually any permutation. Write it as the product of disjoint cycles. You can always do that by theorem, I can't remember which. But in chapter 5, when we're looking at permutations, one of the theorems was that you can always write any permutation as a product of disjoint cycles. In many ways, in fact, but it was always the way. Okay? So you do it. And then, exactly one of these things will happen. Either it's just a 3 cycle, or not just a 3 cycle, and it contains a long cycle, longer than 3, somewhere in the product. Okay? And the rest is, I'm not saying what it is. We don't know. There's some rest that returns it by, it could be the identity, it could be some other cycles, we don't know, but at least one long cycle. And there's no long cycle, and it's not a 3 cycle, it can also happen that you find somewhere 2 3 cycles, as you've written it. And then it looks like this. And you don't know what tau is, but it doesn't contain a long cycle. Or you don't find 2 3 cycles at all, and then maybe you find 1 3 cycle. Now you find 1 3 cycle, you know there's no long cycle, and there's no other 3 cycle, the rest of them have to be 2 cycles. Okay, so tau is the product of 2 disjoint 2 cycles. Or you don't find any 3 cycles at all in the product you've done, and then it has to be only 2 cycles, but you have to have at least 2, because if you only had 1, that's an odd permutation. So you have to have at least 2 cycles in the product. And this could be the identity, or it could be some more, an even number of 2 cycles, we don't know, but at least 2 cycles. Okay? Okay. Now we're looking at each of these cases separately, and we're trying to prove that no matter which of these 5 cases happens, N contains a 3 cycle, because that's what the lemma says. Okay? So case 1, we said was easy. If sigma is already a 3 cycle, then N contains a 3 cycle, and that's it. Case 2, we said if there's a long cycle, then you can work with this long cycle. You can find this element in N, which turns out to be a 3 cycle. Okay? Is it clear now? Now, case 3 is if you have 2 3 cycles, at least, of all the elements of 2 3 cycles in the product of sigma, the product that is sigma, A1, A2, A3, and A4, A5, A6. This is what they are. Okay. Then this element is in N because sigma is in N, sigma inverse is in N. And if you multiply sigma by anything in the group from the left, and anything, and its inverse of the anything from the right, because N is normal, you get something that's in the group. So this is in the group, this is in the group, the product is in the group. in the subgroup thing. So N contains this, and now if you do a similar calculation like this one, you get, guess what you get? You can't guess what you get. You get A1, A4, A2, A6, A3. Does that help? What we know from up there, that if there is a long cycle somewhere in N, then there's also a free cycle, so it helps. Case 4.
Basically, he's proved that by showing that exists, there actually has to be a long cycle. It's a long cycle. It's a 3 cycle.
Right.
Not finding a 3 cycle, a longer accident.
Is the proof.
Hang on. In N.
Yeah.
Okay.
So it's not necessarily the sigma that we started with, but there's a different one. And you know that if there is something that has a long cycle and there's a free cycle. Okay, case 4 is that there is something that only has one free cycle and the rest of them are 2 cycles in the product of sigma. Yeah, all disjoint. In this case, N contains sigma squared because N contains sigma, so it also contains sigma times sigma. So what is this? This is tau times A1, A2, A3 times tau times A1, A2, A3. Now, this and that are disjoint, so tau commutes with this. Disjoint cycles commute. Tau squared, because tau is just 2 cycles, tau squared is the identity. So this is A1, A2, A3 squared. And A1, A2, A3 squared is A1, A3, A2. And the last case, I put down here, it's a tricky case. So this is when you have, remember, this is when you have only 2 cycles, at least 2 of them. I don't know why it's, it is a tricky case. But we have to finish it because I promised Killian that I would finish it. So N contains by the same principle as we've had before, sigma inverse A1, A2, A3, sigma A1, A2, A3 inverse. That's the same thing as before. Now, if you work it out in the same way that we've done, I don't want to waste time doing that because that's not really interesting. You get A1, A3, A2, A3. Okay, so there's nothing, no 3 cycle yet. But now, Now comes the trick. So we know that we have moving it around. So we have A1, A2, A3, A4, these elements we know. We have that we do A1, A3, A2, A4, just the product, just these two cycles, that's in the group. Now, n is assumed to be at least 5. So there exists an element, a number from 1 to n, which is different from all of these. Because we've got 4 numbers there, A1, A2, A3, A4. And n is at least 5, so there must be something there that's not any of these. So because n is at least 5, there exists some b, which is a number between 1 and n, and is none of these numbers, a1, a2, a3, and so on. Okay, and now n contains a1, a3, b inverse, a1, a3, a2, a4, a1, a3, b, a1, a3, a2, a4. This is a crazy element. So where does A1 go? A1 goes to A3, goes to B, goes to A3. Have a look. Where does A3 go? He goes to A1, goes to A3, goes to A1, goes to B. Where does B go? B goes to A1.
A1 goes to A3.
Goes to A3.
Yeah.
Goes to A1.
Yeah. Same as that.
What else is there? A2 goes to A4. Goes to A2.
That's it.
A2 goes to A2. A4 goes to A2. Goes to A2. There's nothing else there? Okay, so it's a free cycle. In all 5 cases, we found a free cycle. Theorem 10, 11. Let n be at least 5, then an is simple. That's what I promised you. Proof. Okay, so what does it mean to be simple?
Yeah,
For a group.
I agree.
That means it's a normal subgroup. But a group, to be simple, it means that its only normal subgroups are the identity, the one element subgroup, and the whole group itself. So we want to show that any normal subgroup is one of these 2 cases. So, okay, so if n is normal in an, then either n is just the identity, or N contains a 3 cycle, which was lemma 1010. But then N is AN by lemma 10.9. That was close. Now, split again, it's lemmas perhaps hides what's going on, but maybe it doesn't quite. So you want to look at what are the normal subgroups of AN? Well, the identity. Yeah, it's one. We take a bigger one, then we just seen that it contains a 3 cycle. If it contains a 3 cycle, we had lemma 8.5, which says that if no, 10.9. If it contains a 3 cycle, then it contains many 3 cycles, and then by previous lemma, if it contains many 3 cycles, it has to be the whole group. So that shows up. If it's normal, it can't be between the identity and the whole group. It has to be one. Yeah. Everything all right? Now you need to digest it and reprocess. Yeah.